subtract instruction. So, we have got this SUB normal subtract and the subtract with borrow. So, that will come as SBB. So, subtract is similar as add. So, it is register 2 register 1. So, register 2 gets register 1 minus register 2. So, like that sorry, this should be register 2 minus register 1. So, this is wrong, this should be register 2 minus register 1, okay, because that is the destination. So, that comes first, and so that way we have got the subtract operation. Next we have got the subtract with borrow. So, here it is fine. So, register 2 gets register 1 minus. So, this should also be register 2 minus register 1. This is register 2 minus register 1 minus the carry flag. Okay. So, otherwise they are same, otherwise it is similar to the add operation. Then increment operation. So, there is you can increment an 8-bit register, or you can increment 16-bit register, or you can increment a memory location. So, this INC instruction. Similarly, we have got decrement operation. So, decrement 8-bit register, 16-bit register, or memory location. Multiply. So, we have got multiply and a register can be specified. So, in this case AX will get AL multiplied by register the 8-bit register, and for word operation DX colon AX will get AX into register 16. Actually, what happens is that if you multiply two 8-bit values, so you get a 16-bit value. So, in multiply operation one of the operand is always the AX or AL register. So, if you are doing 8-bit multiplication, then it is assumed that one of the operands is in AL register, the other one is in the register that is mentioned here, and the result is 16-bit, and this AX register will hold that 16-bit value. On the other hand, if you are doing 16-bit multiplication, then whatever register you mention, so that will be it will be assumed that AX is the other source operand. So, this 16-bit register content will be multiplied by AX, and the result will be a 32-bit content, and that will be stored in DX and AX registers. Okay, so, DX will hold the higher order 16-bit and the AX will hold the lower order 16-bit. So, similarly, we have got this integer multiplication and division operation. So, that way also it is similar to that multiplication division. Then there is div instruction. So, the assumption is that AX divided by the register 8-bit register. So, that will be done. So, that will come to AL, and AH will hold the remainder part. So, quotient part will go to AL. So, AX is the dividend and register is the divisor, and so when this division is done, quotient will be kept in the AL register, and that remainder will go to the AH register. Remainder will go to the AH register. For 32-bit operation, DX AX pair. So, it is expected to hold the dividend that will be divided by the 16-bit register divisor kept in this 16-bit register, and after division AX gets the quotient, and after the DX gets the remainder. So, this way this division operation will be carried out. We have similarly we have got this IDIV instruction. Then there is a comparison instruction. So, this comparison, so it will compare the operands like register 2, register 1. So, it will compare between them. So, if register 2 is greater than register 1, then all this is this will be the setting CF equal to 0, ZF equal to 0, SF equal to 0, and for different if register 2 is less than register 1, then the carry flag will be 1, ZF is 0 and SF is 1. So, this way this comparison will take place. Then other arithmetic operation like the say if register is greater than data, then this will be the setting. So, these are the various settings when we have got this comparison instruction. Logical instructions AND or XOR test, shift right, shift left, etc. So, AND is like just like we had got AND in 8085. So, AND A comma data. So, this is I can have 8-bit data or 16-bit data. So, with AX register they will be ANDed. Or we can have OR instruction, again the same thing. So, OR will be done and register 2 will get register 2 or register 1. So, in this case register 2 will get register 2 or memory. So, like that the OR operation will take place. And then we have got the string manipulation instructions. So, string is nothing but a sequence of bytes or words. So, we can think of it as a sequence of bytes stored in the memory. So, 8086 instruction set includes instructions to for string movement, comparison, scan, load and store. There is an REP instruction prefix, it is used to repeat the string instruction. So, if you want to repeat it for some times, so you can put a repeat prefix before that instruction, and how many times it will be repeated. So, that will be determined by the content of CX register. So, string instructions end with S, SB or SW, where S represents the string, SB is the string byte and SW is the string word. Offset or effective address of the source operand is stored in the SI register and destination is in the DI register. Depending upon the direction flag DF, SI DI values will be updated. So, if DF is 0, SI DI will be incremented by 1 for byte and 2 for word. So, if the instruction is ending with this B, in that case it will be incremented by 1. If it is ending with W, so it will be incremented by 2. So, if DF equal to 0, on the other hand if DF equal to 1, they will be decremented by 1 or 2. So, that way we have got the string manipulation instructions. So, we will see in more detail some more instruction examples. And then this REP flag that we were talking about. So, this REP prefix, so this is repeat this CMPS or scan till ZF equal to 0. So, 0 flag equal to 0. So, while CX not equal to 0 and ZF equal to 1, repeat execution of string instruction and CX will be decremented by 1 every time. And then REP NZ. So, if CX not equal to 0 and DF equal to 0, repeat execution of string instruction and CX will be made equal to CX is decremented. It is done till Z flag is not becomes equal to 1. So, as long as Z flag is 0, so it will be continuing like that. So, this is the first instruction that we have, moves B. So, moves byte. So, what it does? It the first address is calculated, the source address is calculated as DS into 16 plus SI, destination address is calculated as ES into 16 plus DI, then this content is moved to this destination, and after that depending upon the DF flag setting, DI and SI registers are updated. And moves W, so it is also similar to this, only thing is that 2 bytes will be moved, and then depending upon the DF flag setting, DI and SI will be incremented or decremented by 2. Then the CMPS instruction, the compare. So, compare, we have got compare byte and compare word. So, otherwise it is similar to this moves B, but it is checking the it is comparing between the strings. So, if the source string is larger, source byte is larger than the destination byte, then CF will be made equal to 0. So, this will be the flag setting, otherwise this will be the flag setting. So, it will go like this. Then we have got scan a string byte or word with accumulator. So, it is basically comparison with the accumulator. So, it will compare AL value with this content of the memory location, which is pointed to by DS ES colon DI. On the other hand, if this SCASW, so this will compare the word. So, it will be comparing AX register with the 2 successive memory addresses which is pointed to by this ES colon DI, and then DF flag will be depending upon the DF flag. So, this DI value will be either incremented or decremented. Then we have got load. So, it will load the string byte into AL or string word into AX. So, this loads B. So, it will be the source the address is calculated as DS into 16 plus SI, and this AL register gets the content of that memory location. If DF is 0, then this SI is incremented, if it is 1, then SI is decremented, and this loads W. So, this will be moving one word from memory locations into the AX register. So, just the reverse of this loads, we have got STOS. So, we have got STOS B and STOS W. So, this is storing the content of AL register onto the memory address, or it is called storing the content of AX pair onto these 2 memory locations MAE and MAE plus 1. So, that way this loading the storing and loading will be done. So, then we have got a number of control instructions like this STC, like set carry flag equal to 0, So they are 0 operand instruction. The CLC carry flag is 0, clear carry flag. CMC it will complement the carry. STD set it will set the direction flag. Like in the this instruction, so you are telling if DF equal to 0, then this will happen or this will happen. So how to set the direction flag? So that is given by this STD and CLD instructions. Then we have got STI and CLI regarding interrupt flags enable and disable. So we have got this NOP instruction NOP just like in 8085. So you have got halt instruction for it is halt after the interrupt is set, and the wait it is wait for the test pin to become active. So as long as this test pin is high, so it will be remaining in the wait state. When the test pin will become low, then this condition is true, so it will be coming out. Then there is an escape opcode, so that is used for coprocessors. So if you have an instruction which starts with an escape opcode, so the 8086 will pass on the instruction to the coprocessor, and this lock prefix, so that will be lock the bus during the next instruction. So this if you execute a lock instruction, then in the next for the next instruction, so bus will not be released by 8086 to others. So next instruction will be executing in an uninterrupted fashion. So this transfer control to a specific destination or target, and they do not affect the flags. So this control transfers, we have got call instruction, return instruction and jump instruction. So call so this is calling the subroutine. So the address we can directly mention a 16-bit displacement, a memory location address or a register. So the register content will be used as the memory address. In this case, the memory location content will be used as the target address, and here the address is specified directly. And similarly, we have got the jump instruction. Then in 8086 conditional branch instruction, so they will check the flags, and then if the condition is true, the program control will be transferred to the new memory location in the same segment by modifying the content of the IP register. So this we have got JE. So JE displacement a jump if equal. So if the equality condition is satisfied, then the 8-bit displacement is specified. So that will be added with the IP, and that will be making the 8-bit jump. So similarly, we have got JNE or JNZ type of instruction. So there also we have got this 8-bit, all these conditional branches. So they are relative to the IP address to the IP value, the instruction pointer value. So it will be jumping with respect to IP. On the other hand, this conditional unsigned conditional branch. So we have got this JE displacement 8 and the things like that. So this will be executing in a same fashion. Okay, so we have so these values may be unsigned. Okay, so that is there. So conditional branch instruction that can affect flags like JC. So jump if carry flag equal to 1, JNC jump if carry flag equal to 0. So it will go like that. So there are many such conditional branches that are available in 8086 that can be used for doing branching within that. So in this way, in 8086 we find that we have got a much richer set of registers. We have got much richer set of instructions and operations that can be done as compared to 8085. And if you look into these further processors, then the structure will become more and more complex. So all these developments are done starting with the digital circuits, where we know how to design individual logic modules or individual registers, individual combinational functions and all, and from there it is developed towards such complex systems. So that gives a good idea like how we can design complex systems, and what type of complex systems we can, digital systems we can think about with using those basic gates and flip flops.